I'm glad you made it here. We're going to continue with curve sketching today, and we're going to do more examples that are going to go the exact same way that the other examples have been. We're just going to look at different examples. We're going to go through one in this video, and then I'm going to have some example problems that have different functions in them. So let's take a look at our example function here. Let's look at h of x equals x minus 1/6 x squared minus 2/3 ln of x. Okay, so first we are going to note the domain here is not all real numbers because we have an ln of x in it. The domain is going to be from 0 to infinity. So that's an important thing to notice, from 0 to infinity. Okay, once we have that, we can also recognize when we have our ln of x, that is going to have a vertical asymptote at x equals 0. And there are two other terms, but those terms basically vanish as we get closer and closer to 0. So they're not going to affect that limit. They're not going to affect that asymptote. So let's note that we have a vertical asymptote at x equals 0 on the left-hand side of that domain. So these are things that are just helpful to think about when we're going to end up graphing this. So once we've done this, let's look at the derivative, because that will help us find any critical numbers. So f prime of x is going to be 1 minus, the derivative of x squared is 2x, and when we multiply that by 1/6, that gives us 2/6 or 1/3 x. And then we have minus 2/3 times the derivative of ln of x is 1 over x. So that's going to give us 1 over x. This is basically 2 over 3x in the end. And we can combine these into a common denominator, where the common denominator is going to be 3x. So this is going to end up being 3x over 3x minus x squared over 3x. Right, we multiply, this x is in the numerator, and we multiply the top and bottom by x to get our 3x in the denominator. And then that's going to be minus 2 over 3x. And we can combine all of these, negative x squared plus 3x minus 2 all over 3x. We're going to want to factor the numerator so we can see where it equals 0. But that negative out front's a little annoying, so I'm going to multiply the top and bottom by -1 just to turn that leading coefficient positive. And that's just going to make the denominator -3x, which is not difficult to work with. And then we can factor that numerator pretty easily. It's going to be x minus 2 times x minus 1. That's all going to be over -3x. So that is our derivative. If we're looking for critical numbers, the denominator is 0 when x equals 0, but that is not a part of our domain, so we're going to ignore that. That's not going to be a critical number. The critical numbers are going to come from when the numerator is equal to 0, and that's going to happen when x equals 2 and x equals 1. Both of those are going to end up causing the numerator to be 0, which is going to cause the derivative to be 0. We can make a sign chart to see where our derivative is going to be positive and negative, where our function is going to be increasing and decreasing. Remember, our domain starts at 0, and then the critical numbers are 1 and 2. And if we look at that derivative, our factors are x minus 2, x minus 1, and -3x. -3x is always going to be negative when x is greater than 0. X minus 1 is going to be negative, positive, and then positive. And x minus 2 is going to be negative, negative, positive. So the derivative is going to be negative, positive, negative. So we're going to be decreasing, increasing, and decreasing. So we're going to have a local minimum at 1 and a local maximum at 2. We can use a calculator to evaluate the function at those points. We end up with h of 1 equaling 5/6, which is about 0.83. And again, I'm realizing I've used f prime instead of h prime, which is unfortunate. I'm going to erase that and fix it. So that's going to be h prime. And then also down at the bottom, that's also going to be an h. I apologize for any confusion, but I bet you've done the same at some point, and we need to have a little bit of leniency. So, all right, we've got h of 1 is 5/6, and then we also have to evaluate h of 2 for our other critical point. We're going to end up getting 4/3 minus 2/3 ln of 2, which is approximately equal to 0.87. This was a local maximum, and the other one was a local minimum. They're very close to each other in function values, so our graph isn't going to be growing too much in that interval, but it is what it is. And then we'll need our second derivative so we can get inflection points and figure out where the graph is concave upward and downward. So if we want the second derivative, we need to differentiate the first derivative. And I don't want to do it with the factored form because we're going to need the product and quotient rule. That's going to be kind of annoying. I want to use the original form because that's a lot easier for differentiating. So if we want to differentiate 1, that goes away. The derivative of negative 1/3 x is just negative 1/3. And then we need to differentiate negative 2/3 times 1 over x. Well, that's going to be negative 2/3 times the derivative of 1 over x, which is negative 1 over x squared. We use the power rule there. The negatives end up canceling there, and so we end up with negative 1/3 and then plus 2 over 3x squared. And just like the other problem, we're going to combine these into one fraction to make working with it a little bit easier. The denominator is going to be 3x squared, so it's going to be negative x squared plus 2 all over 3x squared. And if we combine that, I'm going to put the 2 out front. I think that'll be a little nicer. 2 minus x squared over 3x squared. Now, this is going to equal 0 whenever the numerator equals 0. And that's going to equal 0 when x squared is 2. And that's going to be when x is plus or minus root 2. But negative root 2 isn't in our domain, so we just need to examine positive root 2 right there. If we make a sign chart for the second derivative, let's do that over here. I'm trying to save some space for the graph of the function. Remember, the domain starts at 0, and then we've got the square root of 2, and our factors there are 2 minus x squared and 3x squared. 3x squared is always going to be positive. 2 minus x squared is going to be positive and then negative, because if x is less than the square root of 2, x squared is less than 2, and 2 minus something that's less than 2 is positive, but then when x gets too big, this becomes negative. And so then our second derivative is going to be positive and then negative. So we're going to be concave upward and then concave downward, and we're going to have a point of inflection at the square root of 2, and then whatever the function value is there, h of the square root of 2 is approximately equal to 0.850 if we're rounding. Okay, and then we can start putting these things on a graph. And I didn't pull the grid lines on here because they looked more distracting than anything else in this particular set of axes. So let's not worry about that. Let's see, what do we have? We have our domain from 0 to infinity. So we're only looking at the right-hand side. We have a vertical asymptote at x equals 0. If it was a positive ln of x, we would know that the vertical asymptote would be going downward, but that term is negative, so we're actually going to be going up along the y-axis as we go towards it. I'm just thinking about how that's going to look. But let's plot the specific points that we have so far. We said that we had a local minimum at 1, 0.83. So that's going to be around here. And then a local maximum just a teensy bit higher at 2, 0.87. Barely noticeably higher. And then we had an inflection point at the square root of 2, which is about 1.4, and then 0.85. So that's going to be right about there. Goodness, that's so close. Those are so close together, I can almost not differentiate them vertically. And then we said that our function was going to be decreasing between 0 and 1, and then increasing from 1 to 2. So on both of those little intervals, increasing, and then decreasing after 2. And then we said it's going to be concave upward to the left of the square root of 2, and then downward afterwards. And so if we look at this first interval, it's decreasing, and it's also concave up, so something like this. And that matches with the fact that we knew it was going to be asymptotically approaching the y-axis. So it's going to look something like this. And then we are increasing on both of these intervals, but we're going to do it concave up and then concave down. Now, this is so close, you can barely tell. I can't even draw it clearly enough, but we are concave up a little bit and then concave down. And then afterwards, we are concave down and decreasing. We have not figured out where the asymptote is, and that's going to be really difficult when we've got an ln of x in here. So one thing that is not going to be accurate on this graph is where the x-intercept is, but we're just going to have to live with that. And this is what we have for our graph. And the points that are accurate are the local minimum, the local maximum, the point of inflection, and then the concavity and increasing and decreasing intervals are all accurate. The asymptote is accurate. It's just this intercept. We don't really know what's going to go on over here, but I think that's okay. We know which parts of our graph are accurate. We know which parts are not accurate, and that is good enough for now.